last thing that we have to learn about. It's just the opposite, pretty much, of what we were doing on Monday. Monday's lesson said revolving around horizontal lines other than the x-axis, so this is just going the other way. Vertical lines other than the y. Now, like usual, I'm going to start out, bless you, with some rules and some formulas and things that you'll want to write down. So it says that title was other than the y-axis, if you didn't quite get that part. But the rule says when you revolve around a vertical line, usually the y-axis, first thing I'm going to put up here is that you need to integrate with respect to y. Just like you would if you were revolving around the y-axis. You would have to integrate with respect to y. So same deal here. So I'm just kind of going in a little bit more detail about this bullet point. When you integrate with respect to y, your function needs to have x equals out front, or in other words, it needs to be in terms of y. So it's got to have y's in the function, bless you. X equals out front though. And also, your upper and lower bounds are now y values. So C is the lowest y value, and D would be the highest. And we're talking the bounds of that shaded region. Wherever that's at, lowest, highest, those become the upper and lower bounds on your integral. Okie doke. Now, here is the setup for revolving around a vertical line other than the y-axis. It's still basically the same as Monday, except for the dy part and the c and the d. It says pi times the integral from c to d, just talked about those, of the outer radius squared minus the inner radius squared dy. Now, because we're spinning around a vertical line instead of a horizontal line, where the outer function is and the inner function is going to be a little bit different. But I'm still going to basically keep this part the same. You get the outer radius from finding the distance between the axis of revolution and the function defining the outside of the washer. It's going to look different today though, again, because it's a vertical line. And on the other side there, I'm just going to put basically the same thing except inside of the washer. Distance between the axis of revolution and the function defining the inside of the washer. And one last thing to put up here, that distance that we're talking about right here, I kind of just underlined it a little too far up, there we go. The distance that we're talking about is found by taking the function itself minus the axis of revolution. That is the same as Monday, but again, the washer is going to look different because we're spinning around a vertical line. Okie doke. And I'm going to go ahead and put just a little visual up here of what this is going to look like. You don't have to copy this down, but I'm going to put my rectangle here. It looks like it kind of got covered up. you can see the axis of revolution right here. I'm not sure what it is exactly, but it's a vertical line. And remember, the rectangle always has to be perpendicular to the axis of revolution. So that's how I knew to draw it this way instead of up and down. So imagine this rectangle spinning around that axis of revolution. It's no longer going up and around, so the washer is no longer going up and down. The washer is now kind of flat. If you spin this around, it's just going to be a washer sitting like this. This right here is going to form that circle in the middle, the inside. That is going to end up being the outside of the washer. So that's kind of what we have to pay attention to when we set up the integrand. Which one is inside and then which one is outside. All right? Don't worry about getting all of that down, because once we do our examples again, we'll draw the pictures and we'll try to visualize that again. So, quiz tomorrow. I am going to put in the directions to sketch a graph first. I know that hasn't really been specific in our notes in this section, but it will make up part of your points on the quiz. So it'll say sketch a graph and find the volume of the solid generated by revolving the region around the given line. We're going to sketch the graph first. Okie doke. And I think we'll have 2 examples today, just kind of like we had 2 on Monday. And keep in mind, the axis of revolution today is going to be vertical, so we have to integrate with respect to y, just like we did with the y-axis. Alrighty, so here is example 1. It says y equals the square root of x, y equals 0, x equals 4, and we're supposed to spin around x equals 6. That last part is our axis of revolution. Okay, well here I go. I'm going to start to sketch those functions first. X equals 4, 1, 2. Actually, I got to go all the way to 6. I might want to make this a little bit tighter here. 1, 2, 3, 4, 5, 6. That should be enough on the x-axis. And I don't think you really have to go up very high on the y-axis. But this is our parent graph of a square root. It's going to start at the origin, and it's going to sprout. So 1, 1 would be our next point. 4, 2 is the next nice point. And I'll probably stop the square root graph right there, because if you look at that third equation, it says x equals 4. So that is going to be a vertical line at x equals 4. I guess if you want to draw the whole thing, you can. But it's going to get cut off on bottom by y equals 0. So it's that horizontal line right at 0. This is the region that we have bounded in. And I'm going to put my axis of revolution up here before I decide how to draw the rectangle. Axis of revolution is at x equals 6. So right there. And like we mentioned earlier, or really we've mentioned this whole section, the rectangle has to be perpendicular to the axis of revolution. It's going this way, so my rectangle, kind of like I showed you earlier, needs to be on its side, more horizontal, so it's perpendicular to the vertical line. Okie doke. Again, I'm spinning this around the line x equals 6. The washer is going to be flat once you do that. It's no longer going up and down. Now, like I've always said, the setup is the most important part. So I've got pi out front still. That has not changed. But now, keep in mind, we are going to integrate with respect to y. And I mean, on your quiz tomorrow, some of them will be with respect to y, some of them will be x. I don't tell you that part. That's something that you have to know. If I'm spinning around a vertical line, like the y-axis, then I need to integrate with respect to y. Or if I'm spinning around a horizontal line, like the x-axis, we would integrate with respect to x. Now, the bounds have to be y values, so don't put 0 to 4 up there. It's actually going to be 0 to 2. Again, we're integrating with respect to y. So 0 to 2. And I've got to put the outer radius squared minus the inner radius squared. And to get, I'll start with the outer radius. To get the outer radius, bless you, I want to take the function that forms the outside of the washer. So in this case, it would be our square root function. I want to take that minus 6 because that was our axis of revolution. Now, would it make sense if I did that, square root of x minus 6? If I'm going to integrate with respect to y, I don't want that to have x's in it. So let's go ahead and solve this real quick for x. We would just need to square both sides. That'll take care of the square root. And now it says x equals y squared. That is the function that forms the outside of the washer. Okay, minus, may have to scoot that down a little bit, the inner radius squared. Okay, this right here, if I spin this around, this part forms the inside of the washer. That function is 4, just 4. It already had x out front. And we have to subtract that function minus the axis of revolution. It's a lot of the same steps as Monday, but again, only main difference is that you have to integrate with respect to y because it's a vertical line like the y-axis. Now, any questions about the setup first? Most important part there. I'm going to come down here for a second and FOIL the y squared minus 6 squared, and then I can plug this back in. I'll get y to the 4th minus 6y squared minus another 6y squared plus 36. So if I go ahead and put that back in for that first part, let's make it y to the 4th minus 12y squared plus 36. Now, I'm not done yet because I still have to simplify this part. I'm still supposed to subtract 4 minus 6 squared. Now 4 minus 6 is negative 2, and if I square the negative 2, I get 4. However, that minus sign still needs to be in front. You don't want to take the 2 minuses and make a plus, because exponents have to come before subtraction. Now, I'm going to try to save a little bit of room up here. I'm going to go ahead and take the 36 minus 4 to make that 32. So that is what I have to integrate. Let's keep going here. Keep pi out front. Add 1 to your power. Put your new power on bottom. Minus, this is going to be 12y cubed over 3, but I can simplify that to be 4y cubed here in a second, or negative 4y cubed, plus 32y, and I'll go ahead and maybe simplify that middle term real quick before I plug anything in. Y to the 5th over 5 minus 4y cubed plus 32y. And we've gotten pretty lucky recently. Our lower bounds a lot of times are 0, not always. But plug in a 2. 2 to the 5th is 32, so that's like a 32 fifths. Minus 2 to the 3rd power is 8. 8 times 4 is 32. Plus 2 times 32 is 64. So let me add all of those up, and it actually works out kind of nice. I get a 38.4 pi. And you can put units cubed if you want on there, since it is volume. Alrighty, outer radius squared minus inner radius squared. Same idea. Questions about the first one? Okey-doke. Now, this is the only other example we're going to do, but may require a little bit more work, at least to kind of get the graph drawn. It says x equals y squared minus 1, x equals 3, and we're supposed to revolve around x equals 4. The fact that this has x equals out front is going to be helpful when I go to set up my integrand, because this already has y's, so I'll be able to just plug that right in. However, it's not very helpful when I try to look at the graph. So what I'm going to do real quick is I'm going to solve this for y, only so I have something to type into my calculator. All right, I'm going to add 1 to both sides. That says x plus 1 equals y squared. Square root both sides. Now technically, I would need that plus or minus out front. So it says y equals plus or minus the square root of x plus 1. Okie doke. Now, when I put my graph right on top of that, so I may just recopy that function off to the side. When you go to graph this, I mean, you could probably figure out what the graph looks like without your calculator, or if you do still use your calculator, one of your functions can be just the square root of x plus 1. The other, just type in negative square root of x plus 1. Once those two are on the same coordinate plane, that is this function. So it's the same thing. You may just have to type it in a couple times. Now, really, I'm going to erase this real quick so I can put my coordinate plane up here. This is really just the square root. I'm going to put it maybe down here. It's a square root function shifted left 1. So I don't think this would be too hard to graph just knowing that. I'll go ahead and do the positive square root of x plus 1. I'll have a point right here at 0, 1, 1, 2, 3, 4. If I plug in a 3 here, that would be 3, 2. Square root of 4 would give me a 2. Now, that's part of our graph. I'm going to also come down here a little ways to graph the other one. Negative square root of x plus 1 is pretty much that first graph, but flipped upside down. So you've got one part on the top there, one part on the bottom. I cut it off at x equals 3 because I can already tell that since I have a vertical line at x equals 3, this is going to be my bounded region. This is what I'm going to have to spin around. Now, coloring quickly here, once I get my axis of revolution drawn, I'll put my rectangle, and then I'll know where to put my rectangle. X equals 4. There's the axis of revolution. So again, the rectangle, wherever you put it, needs to be on its side. Has to be perpendicular to the axis of revolution. And by the way, whenever we do spin around vertical lines other than the y-axis, all of ours are going to be vertical lines on the right side of our shaded region. So you can pretty well count on this. When you set up the outer radius, it's always going to be the function on the left. And the inner radius is always going to work with that function on the right. Because again, I'll go ahead and just tell you, all of your axes of revolution that are vertical should end up being somewhere on the right. Okay, now I'm integrating with respect to y, so lowest y value and highest y value. Kind of a bummer that it's not 0, but we'll have to integrate from -2 to +2. And here we go. Function that forms the outside of the washer, which was this function, already solved for x, so that is nice, minus the axis of revolution, which is 4. I'll have a little bit of simplifying to do with that in a second. Now, the inner radius, the function that forms the inside is x equals 3. And so I'll subtract the axis of revolution again, which is 4. Now, the first part in parentheses is going to end up being y squared minus 5 squared. So I'll come down here for a second and figure out what that actually is. Foiling, I'll have y to the 4th minus 5y squared minus another 5y squared plus 25. So when I plug that back in, I'll want to combine my like terms, and I'll just make this y to the 4th minus 10y squared plus 25. Now what am I going to be subtracting after the 25? What would this end up being? Just a 1. Yeah, 3 minus 4 is -1. -1 squared is 1. So when I take the 25 minus 1, I'm going to go ahead and save some room and turn that into a 24. Okie doke. And here we go. Add 1 to our power. Put our new power on bottom. Minus 10y cubed over 3 plus 24y. And again, it is a little bit of a bummer because our lower bound is not 0, so I'll have to do both numbers on this problem. There's quite a few negatives that we have to worry about, especially when we go to plug in the -2. So let's be extra careful with those, but I'm starting with the positive 2. 2 to the 5th power is 32, so that's going to be 32 over 5, minus, got to do my exponent first here, 2 cubed is 8, 8 times 10 is 80, so I'm going to leave that as a minus 80/3. Plus 48. 24 times 2 gave me the 48. Subtract what you get when you plug in the -2. Now remember, a negative number to a power, to an odd power I should say, is still negative. So -2 to the 5th is -32 fifths. I will have to distribute my negative in a second, but I'll get there in just a minute. Minus, now let me think about this real quick. -2 to the 3rd is -8. By the time I take -10 times -8, that should end up being a plus 80/3. And then 24 times -2 is -48. So I'm going to distribute the negative sign real quick and then just hopefully type everything into my calculator. This is going to be plus 32 fifths minus 80/3 plus 48. I'm just using parentheses on my calculator to keep those fractions together. 32 fifths minus 80/3 plus 48 plus another 32 fifths minus 80/3 plus the last 48, and it should be like a 55.5 pi. Just rounded it off to 1 decimal place. 55.5 pi. Alrighty. Only reason we solved that for y earlier was to get it graphed. I was integrating with respect to y, so that's why we went back and used the y squared minus 1. Any questions about example 2? Okie doke. We've learned a lot in section 6.2. So this is C99. We're getting up there. From page 426, we are just doing 2 problems again, 21 and 22.